Okay, let's talk about the boundedness of the same sequence. We just showed that it was a monotonic increasing sequence, so we know it's increasing. And we know A1 we can calculate by putting n equals 1, and that looks like it gives us -1/7. We could have pulled this from our calculator as well, and we know from there on it's going to keep increasing. Each next term is going to get bigger and bigger. So we just want to know if it's bounded above also, because this tells me that if it starts at -1/7 and keeps increasing, then it must be bounded below, because everybody else is bigger than that. So it's bounded below by, let's say, that very first term, -1/7. Now, is it bounded above? Is the question. Well, I can just go analyze this a sub n. A sub n is 2n minus 3 over 3n plus 4. If I want to analyze what happens at the right end, I can say, well, what if I ignore this -3? What if I compare it to this guy? If I compare it to this guy, which one of these is smaller? It has to be this left side because they're identical, but the left side has a smaller numerator. So again, if the denominators are the same and the numerator is smaller, then the left side's got to be smaller. Then I can say, well, let me make one other change. What if I keep the 2n the same and eat up the 4 from downstairs? Well, if I do that, then again, the left side has to be smaller because notice this denominator is now bigger. So I'm dividing by something that's bigger. So if I'm only focusing on these two guys, then equality should be, well, this guy has to be smaller because the denominator of this is bigger than this guy. And 2n over 3n is just 2/3. So you can think of it like that and say, yeah, all the terms of this sequence, regardless of what n is, are always going to be bounded above by 2/3. So it's bounded below and it's bounded above, and we also showed that it was monotonic increasing, so this sequence for sure, using that theorem of course, converges because it's monotonic and it is bounded. Now this is a simple one that we can analyze even without boundedness and monotonic saying it increases, because we could actually find the limit of that sequence. The limit as n goes to infinity of this guy is not so bad. 2n minus 3 over 3n plus 4. Of course, if we divide by the highest power in the denominator, or even apply L'Hopital if we're formally showing it, this is what we're going to end up with. And of course, we're taking the limit as n goes to infinity, so this guy goes to 0, that guy goes to 0. And we actually know for sure this one converges to 2/3. But theoretically, sometimes you're not able to find the actual limit, but you are able to show these other two ideas where something is monotonic and it's bounded, then you know for sure that whether you can actually find what it converges to or not, that the sequence will converge. Is this sequence bounded? Well, my sequence seems to be somewhat of a boring sequence. If n is 1, let's see what happens, 2, 3, and so forth. If n is 1, I get -1 to the 2, I guess, and that's a positive 1. When n is 2, I get it to the 3rd, it spits out a -1. When it's 3, I get it to the 4th, so it spits out a positive 1. So it looks like the terms of my sequence just oscillate back and forth between 1 and -1. So my sequence is this sequence. Is it bounded is the question. Well, yeah, the terms of the sequence never go past 1, and they never drop below -1, so our answer would be yes, it's really bounded below by -1 and above by 1. Now, does this sequence converge? Let's ask that question. Well, if I'm looking at the limit as n goes to infinity, because I'm talking about convergence, of this guy, this is just going to keep oscillating back and forth between 1 and -1 and never get arbitrarily close to either one. So this would be that it diverges since the terms just oscillate. So it doesn't go to one specific one and it diverges. Now that doesn't really violate the theorem we talked about earlier because this sequence is not monotonic, it's only bounded. If a sequence is only bounded, it doesn't necessarily mean that it's going to converge. It has to be both increase or decrease along with bounded to show that it converges. So in this case, it satisfies the bounded criteria, but it's not increasing or decreasing, in other words, monotonic, and it turned out that this thing diverges. Question here is, let's call it part A, is the sequence monotonic? Well, A1 is 2 to the 1, A2 is 2 squared, which is 4, A3 is 2 cubed, which is 8, and so forth. So it seems like the sequence is increasing, and hence it is monotonic. So our answer is yes. And if I want to formally show it, the next guy compared to my current guy would be 2 to the n plus 1, and this would be 2 to the n, and I can use exponent laws to write it as such. And notice the left side has to be bigger than the right side always because I'm multiplying it by 2. I'm doubling what I was looking at before. So it is increasing, it's monotonic. If I say, does it converge? Is the sequence convergent? Well, if I'm asking about convergence, then I'm looking at the limit as n goes to infinity. And in this case, 2 to the big is actually going to be big, and you would say no, it diverges, since in this case it's that r to the n business we were talking about. R to the n goes off to infinity if r is not, you can say, between -1 and 1. So even though the sequence is monotonic, it's strictly increasing, it's not convergent because it just goes off to infinity in this case. So boundedness and monotonic together imply convergence, but one of them alone doesn't suffice because it could either oscillate, as we saw in this example, back and forth and yet be bounded, or it could be monotonic, increase or decrease without bound, and not converge to anything.